All right, welcome everyone to this little lunch session about graphs, about graph databases. So I thought we'd actually kick it off by checking the temperature in the room a little bit. How many here have heard of NoSQL? Hands up. How many here have heard of SQL? Hands up. How many here have put a NoSQL database in production? How many here have put a graph database in production? Probably 5, 6 people, something like this. All right, sweet. So we have a tight agenda today. I'm going to start by zooming out a little bit and talking about the NoSQL space, after which I'm going to dive into the topic of the hour, which is graph databases, and talk about the fundamentals. I'm going to talk about one specific graph database called Neo4j, which is the one produced by my company. And then we're going to dig into some real-world examples where Neo4j and graph databases are used today. Before that, though, my name is Emil Ephraim, and I have only one ground rule, really, for all of my talks, and that is that I do not want your undivided attention. You're all online. Well, some of you are online. I'm not sure how great the Wi-Fi works. It always seems to be a problem at Java 1. But most of you are online, I hope. So do tweet about this. The only thing that I ask you about is that you use the Neo4j hashtag. I monitor that one religiously. Give me feedback. Let me know if it's interesting or not interesting, if I'm doing good or bad. Also, let's keep it interactive. Feel free to just interrupt me if you have any questions. If they require a more thoughtful response, I might push it to the end. But let's keep this as interactive as possible. So graph databases are being lumped into this whole NoSQL category, which is this big phenomena. I mean, I think 95% of you raised the hand when I asked if you'd heard of NoSQL. It's definitely one of the buzzwords that one can get a little bit tired of. However, I'm going to start by orienting you in NoSQL and let you know where I feel graph databases fit in this broader scheme of things. But before we do that, let's talk about the name. So let's just get the fundamentals down. We all hate the name. The name is horrible. The name talks about something by defining what it's not. NoSQL, right? And a lot of people think that it means no to SQL or never SQL, and that it is a replacement strategy for relational databases. That was never the intent. Most specifically, it was never the intent when you speak at Oracle Open World. And it's, of course, never the intent. And we're all super good friends with relational databases. Because the whole point, actually, is that NoSQL means not only SQL. And it is the observation that the era of the one-size-fits-all database is over. We're now at a point where, for most interesting projects, where we can no longer just assume that we're going to take all of our data and just lump it into one relational database. But we're going to look at the polyglot persistence world, where we're going to look at our big data sets, because all data sets will be big. And we're going to see that this data over here is very messy and complex. Let's put that in a graph database. This data over here is very key value oriented. Let's put that in a key value database. This data over here is very tabular. Let's put that in a relational database. Polyglot persistence, the backends of the future will consist of not only SQL databases, but graph databases and key value stores. So then why did NoSQL happen now? This seems like a good idea. Let's use the right tool for the job. I mean, that's sort of that's our responsibility as engineers. But for some reason, for 40 years, irrespective of the problem, the right answer has always been the relational database. And that's sort of how we as an industry have acted up until 2009 when this term NoSQL was coined. And there are a couple of things why that happened just now. One of them is what I think you've probably seen in many presentations. People talk about this exponential explosion of data. You know, big data is even more hyped than NoSQL. I think Eric Schmidt went on record by saying that every 2 days we create as much information as we did up to 2003. I don't know if that's true, but what is true is that there's an explosion of data that most of us have to cope with and handle. So that's one driver for why all of a sudden we're looking at alternative databases. Another driver is a little bit more subtle, I think, and that's an increase in connected data. It's obvious in the social domain, social data. People even talk about it as the social graph. But it's actually apparent in a lot of other situations as well. The third reason is semi-structured data. Hands up, who here has heard of semi-structured data? Yeah, so most of you. It's basically data where you have a few mandatory attributes and many optional attributes. And that's a challenge to model in a relational database. It can lead, and it often leads to so-called sparse tables, which are basically tables where you have a lot of gaps in the columns of many rows. And the fourth one is a little bit more subtle again. It's a trend in architecture. I don't want to use the amazing SOA word here, but we are, as an industry, moving more from a word of a monolithic architecture where there's a three-tier architecture where you always have a presentation layer and a business layer and a relational database, and that's it, and every system looks like this, to a more services-enabled architecture, right, where you say that, hey, this service over here handles accounts. Let's wrap that in a domain-oriented layer that speaks maybe RESTful service over the wire or something like this. And if you encapsulate your architecture in these kinds of services, all of a sudden you can swap out the persistence backend. Whereas when I got started as a programmer in the early 90s, if I had to change my database, which was a relational database always, that cascaded out across hundreds of applications at my first job. Because all of these applications were tied to the one relational database, of course, happily supplied by Larry. So that's another reason why we can look at alternative databases today. So NoSQL has sort of this curse of being very hyped, so every project wants to call themselves NoSQL so that they can join the NoSQL tracks at conferences and whatnot. And there seems to be a new NoSQL project still announced every week. But if you squint a little bit, you can see that there are 4 broad categories of NoSQL. I'm going to really quickly take you through all 4 of them before we zoom in on graph databases. This is usually a 1 or 2 hour talk that I do, so I'm going to go super, super quick. If you have any questions, though, feel free to hit me up either now or afterwards, even specifics about the other models, not just graph databases. So the first category is key value databases, and they were all inspired by Amazon, who published a white paper or actually an academic article in the mid-2000s called Dynamo. And they said, hey guys, we've been able to take our system and push it to lengths beyond what most people have done. And we have done this not by throwing away the relational database, but by building a new system that we augment the relational database with. And we call it Dynamo, and it's basically a big distributed hash table. Imagine, java.util.map, but like on a system where you can add things over the wire, right? A big distributed hash table. Examples over here is Redis, Riak, Project Voldemort, famous key value stores. Have a bunch of strengths, in particular a very simple model, which makes it super simple to scale it out. There's no connectivity. You have a key and a value pair. That's it, nothing more. And if you have a very simple model like that, you can't take a complex data set and put it in there. But on the other hand, what you can do is that you can say that, hey, this key value pair should reside on this server over here, and this key value pair on this server over here. And it's very simple as an infrastructure provider, as a vendor of a key value store, to build a horizontally scalable solution. The drawback, however, is what I just mentioned. The model is incredibly simple. What I typically, the algorithm that I make is that what if in Java, the only data structure you had available to yourself was a hash table? For int I, no, there's no int. For get something from the hash table, and then you keep working like that. There would be no data structure at all other than this. It would be very awkward to program, and that's what working with the key value store is like. It's very painful. But it has great scalability. So that's the first category. The second category, column families, and they were all inspired by a system called Bigtable. And so Google also published an academic paper saying, hey guys, we've also been able to push our systems to some scale. And we did this by not throwing away the relational database. They're an infamously huge user of MySQL, Google is. But by building a new system that takes over some parts of the relational database's previous responsibilities. And they called it Bigtable. And the data model here is creatively that of a big table, where you have every row can, at least in theory, have its own individual schema. Famous implementations here, Cassandra, I would say, is the most popular one. HBase out of the Apache Hadoop project is definitely rising in popularity. And in terms of strengths and weaknesses, One of the big things about this one is that it can store this semi-structured information, i.e. if you have one row which has, where you would want as a programmer to add maybe 15 columns to it, 15 attributes to it, but most other rows have only 3, you can easily model that in a column family. However, it's very challenging to do secondary indexes. You can really only, at least easily, look it up by primary key. And it's very, very challenging to do connected data. And if you write object-oriented systems, you know that a lot of data is actually very, very connected. The third category is by far the most popular one and the most well-known in the NoSQL space. Here's where MongoDB lives. I would wage, I'm not going to do a hand raising in, but I would wage that probably 90% of you who said that you've put a NoSQL database in production is using Mongo. So this is by far the most popular one. And its heritage is actually, believe it or not, but Lotus Notes. And while Lotus Notes, I'm not sure how many of you have been had the pleasure of using Lotus Notes as an email client. It's probably not the best email system in the world, but it actually had a very interesting architecture, and it had a very very fascinating data backend that Damien Katz, the founder of CouchDB, he worked on that. But he said that, hey, let's take this thing and let's upgrade it to the modern world, which means let's put a RESTful API on top of it. Let's add MapReduce type queries written in JavaScript. And of course, let's write it in Erlang, because that's the language that was cool back then. Of course, now Erlang is not cool at all. Now Scala is the cool language. Or is it Go? I don't know. So anyway, so that's what he did, and that inspired this whole thunderstorm, I would say, towards document databases. And the data model here is that of simple documents. And what they call documents is basically key value pairs, a bunch of key value pairs lumped together, like a JSON document, or like a hash map in Java. Famous implementations, CouchDB, MongoDB, Couchbase, which is a fork-ish of CouchDB. Ask me more about that if you're interested, but it's fork-ish of Couch. Strengths, it's a super simple model. If you understand JSON, which I'm a Java programmer by heart and by training, and so I almost understand JSON. But most programmers out there do very, very natively understand JSON. Then it's super simple. You just take a JSON document, you dump it into your database, and you're done. It's very, very, very simple. It's also easy to get it to scale. It's challenging to model connectivity, which is a good thing if you want to build horizontal scalability. However, it is challenging to model connectivity. And it turns out that a lot of data sets are connected. So in Mongo, what you frequently see is a bunch of key value pairs where the value is an ID of another document. And of course, that's not a first-class citizen in a document database, which means that, for example, if you remove that document, you're going to have a bunch of IDs just pointing to nothingness, to dev null, right? And there's no tangible way to say there's a type between this document and this document. They're connected via, do they know each other, or do they own each other, or whatever it is. So it's a challenge to model connectivity. And then we have graph databases, and I'm not going to go through this at such a high level. I will pay some homage to my lovely competitors and friends in the graph database space. Neo4j is the one that I represent here today, but there are plenty others. One called OrientDB, which is Apache licensed out of Italy. Infinite Graph is probably the second most well-known after Neo4j, and it's based here in Sunnyvale. Allegro Graph comes from the Semantic Web, RDF community. These are all fine graph databases, and I truly urge you to check all graph databases out. Well, maybe not all, but check several graph databases out. However, for the remainder of this talk, I will be focusing on the one that I know really well, which is Neo4j. So before we go on to talk specifically about graph databases, here's one final slide that sort of summarizes NoSQL space. Because it turns out that when you look at the NoSQL space, a lot of people think a lot about scaling to size. But there are actually two axes of scalability. One is scaling to size. How does your system cope with more and more data that looks sort of similar? And the second one is scaling to complexity. How does your system cope with more and more data that is increasingly semi-structured and increasingly connected? And you can see how these four categories are distributed at a very high level. You have the key value stores that are awesome at scaling to size. We talked about the ease of horizontal scalability when you have very detached small key value pairs. We have the column family stores, better at handling connectivity because they can deal with semi-structured information. We have the document databases, even better at dealing with complex stuff because they can store nested documents in and of every document. And then graph databases take it to its most extreme and is amazingly awesome at dealing and modeling complex, connected, semi-structured, and hierarchical data. However, it is the category that is the most hard, that it's the hardest, I guess, to get to scale to size. Because fundamentally, the enemy of horizontal scalability is connections. And graph databases fundamentally embrace connections. They say that, sure, we can take a data model which doesn't allow you to represent connectivity, but the world is connected. So why not embrace that and have a model that can represent that really, really well, and then let us as the vendor, as the infrastructure provider, deal with the horizontal scalability. Of course, my very subjective, and remember again, I'm the graph database guy, but what we see very, very clearly when we're out talking to customers is that 90% of the use cases live substantially below the scalability, the size scalability requirements of all of these systems. Key value stores are great if you want to scale from 10,000 machines to 11,000 machines. But most people actually have maybe 2 to 3 machines or 5 machines. That's more the more high volume, not high volume. What do you mean? The more common deployment scenario is single-digit machines rather than single-digit thousands of machines, and that's why we choose to be a graph database. So that's a crash course on NoSQL, and no questions so far, which means that maybe it was super clear or maybe it wasn't clear at all and you don't dare to ask any questions. But I'm, again, happy to take any questions afterwards on NoSQL as a whole. All right, so graph databases. What are graph databases? So graph databases also sort of have a little bit of an unfortunate word, because when you say graph, a lot of people think of charts. They think Excel, x-axis and y-axis, that kind of stuff, right? But that's actually not what we're talking about. We're talking about that old thing that Euler, that old bearded mathematician in the mid-1700s, invented as a discipline of mathematics. So basically, you model data using nodes, typed relationships between nodes, and then key value pairs that you attach to both these nodes and to the relationships. And we'll get more to this later. Yeah. An interesting point is that if you remember linked list and trees from your data structures classes, the graph database is the most general purpose data structure that at least I've been able to figure out. You can model any other data structure as a subset of graphs. In fact, if you step back into the database world again, it turns out that document databases are a subset of graph databases, because every document in a document database is just a node in a graph database, because the nodes can contain key value pairs. So they're semantically the equivalent thing. But on top of that, you also have these relationships that tie the documents, or the nodes, as we call them in the graph database land, together. So this is how one of my guys typically describe the difference between a relational database and a graph database. A traditional relational database may tell you the average age of everyone in this room. That's a great operation for a relational database. But a graph database will tell you who's most likely to buy you a beer. And I'll dig into a little bit more into that specific example later, actually. More specifically, we're talking now about a graph model called a property graph. And that one looks like this. It has 3 core abstractions. The first one is nodes, and there's a bonus one. But the first one is nodes. The second one are these relationships that connect the nodes together. And then we have key value pairs that you, again, can attach to both the nodes and to the relationship. And the most important point, I think probably the most important point of this entire presentation, is that the relationships are first-class citizens. What the graph database guys like me say is that, hey, how data is connected is such a fundamental aspect that you should embrace that completely and represent that as a first-class citizen. That means that if you code in Java, there's going to be a relationship class, or an interface actually, but you're going to be able to get a relationship type back, a relationship instance back. And on that, you have the same kind of java.util.map-like interface as you have on the nodes. On the nodes, you can add properties: name Andreas, job talking, name Peter, job building, key value that you can attach to the nodes. You can attach the same thing to the relationships. Super powerful. can express that I've spoken at Java 1 and then add the years I've spoken in 2005, 2006, etc. Very, very powerful. And in fact, if you zoom out a little bit and become, the level of philosophical that I actually won't be until you pour me a bunch of beers tonight. But my philosophical view on this is actually that knowledge is all about how you relate things to one another. The fact that my name is Emil doesn't really tell you a whole lot, but the fact that I am Swedish, that I live in Menlo Park, that I work at Neo Technology, that I'm married to Madeline, all of those relationships is what gives me context, what gives me color. And that is what makes you understand who I am. And that's why we try to embrace this whole relationships as first class. There's also a bonus one, which is indexes, because it turns out that in the real world, that's sort of the fluffy description, right? But in the real world, when you sit down and you program with graph databases, you need to get a hook. You need to say that, hey, give me all of Andreas's friends, or give me all the jobs that Allison has had, right? Well, you need to start somewhere. And there's an index to be able to do a lookup where you go from the string Allison down to this particular node. And after that, it's all fundamental graph operations like traversals. So just to really drive home the point, most of you are probably familiar with a relational database. And what in a relational database would be a join table. So typically, one table with 2 columns, ID to ID, or 3 columns, ID, ID, and type, is what fundamentally becomes the relationships in a graph database. I think I already talked about this, the fact that the graph model is a superset of the document model. So anything that can be easily represented in a document database can be equally easily represented in a graph database, which is interesting. So that's on the modeling side. However, performance is also not unimportant. I want to walk you through one particular scenario. We were contacted a while back by a large social network that you've heard about, which said, there are a lot of NoSQL databases out there. We've looked at a gazillion of them. We find them very fascinating, but then we found graph databases. And graph databases are awesome because they allow us to model the world the way the world is. They truly represent the real world in our data. So we really like them. However, we're big social network X, so the only thing that we really care about is performance. So they said, hey, can you show us some benchmarks so we know how fast you are? And us being the honest Swedish geeks that we are, we said, hey guys, we can prove anything with benchmarks. So how about you give us a scenario that is relevant for you, and we'll show you how fast we are in that scenario. So that's what they did. So the scenario they came up with was, let's imagine that we have a social graph, the 1,000 people, 50 average friends. We grab 2 people at random, and we check if they're connected, not even how, but if they're connected. We limit it to depth 4 because otherwise, Kevin Bacon, everyone is related to everyone else, right? So it's limited to depth 4, and we do this with warm caches. So we ran this with a famous Swedish open source relational database, which shall remain unnamed, with 1,000 people, and we grabbed 2 people at random, and it was a 2,000 millisecond operation. Can you guys visualize the schema here? In a relational database, it would be 2 tables. One would be persons with ID and name. The other one would be friends, which links ID to ID. And it's a bunch of joins in that join table. This turns out to be what I call the sweet spot of suck for SQL. It's an arbitrary path length query. You don't know ahead of time. If you grab one person over here and another person over here, you don't know ahead of time how far away they are. So you're going to have to represent that in a really, really awkward, I think it ends up being 32 joins. Super awkward. It's 4 pages of SQL code. It is a horrible, horrible thing. In Neo4j, this was a 2 millisecond operation. So we were pretty happy about that. 1,000 times faster. Sounds about right. But it's also what we're supposed to be good at, right? This is connected data. This is exactly our sweet spot. Not sweet spot of suck, but sweet spot of success, right? So we upped the ante a little bit. We added 1 million persons. This is running on my previous laptop, the one laptop that worked on projectors, which my current laptop doesn't do, which is why you don't get fancy animations here, but just a PDF view. and with a 300 megabyte heap. So, JVM, 300 megabyte heap, pretty small. Added 1 million persons to it, 50 average connections, so 25 million total connections. Grab 2 people at random, and we're still at 2 milliseconds for this one. So when it comes to scalability and performance on ever-increasing complexity of connected data, graph databases are pretty damn awesome. So that's sort of the runtime characteristics. How then would you work with this from a programmatic perspective? Well, this is one example. We have the same social graph that I listed before. And what we want to do here is we want to check the friends of this guy over here called Andreas. Friends of friends, not direct friends, but 2 hops out. And the first thing we do is that we declare a variable called n, because I guess we're poor at naming variables. It should be called Andreas, probably. But anyways, and we do that by using an index lookup. And then the second thing is really important. The second thing is what we do then is we declare a small pattern that we want Neo4j to find in the graph. And this pattern is, of course, represented as ASCII art, obviously. For those of you who are old hackers, you'll recognize that this is obviously the ASCII art of a graph. The first one says that it's a node, which is why you'll see the parentheses. And then you see the relationships indicated by an arrow to an unbound variable, another node, and then another relationship to a variable that we call fof, friend of friend, right? And that's the one that we return. So if you look at Andreas over there, you can see that the first variable will be bound to be maybe this is too small for you, but the closest friends. And then the second variable are bound to the ones that are 2 hops away. So that's a simple way of expressing, give me my friends 2 hops away. This query language is called Cypher. And Cypher is the key way of how you want to interact with the graph database, or at least with Neo4j. And it's a pattern matching query language. So it's similar in philosophy to SQL, but it embraces patterns. You describe these small patterns, you draw them with ASCII art, and then you tell Neo4j to go find them in your big graph, right? So a couple other examples. Let's get the node with ID 0, super simple. Just start, get the node, and then return. Previously, I added a match in there, and the 3 fundamental operations are start, match, and then return. So if we want to traverse from node 1 and 1 step out, we would do something like start from A, and then do a match, which is super simple, from A to B. Hopefully you can see the ASCII art here, and then return B. Or friends of friends, that's the one that we just did. Start from A, go to someone that we're not going to return, so we don't need to have a variable there, and then another hop out. Pretty simple. And if you do this, actually, so I talked before about the sweet spot of SOC for SQL, which is the arbitrary path length queries when you don't know ahead of time. You just represent that by adding a star here. Give me give me the entire path between A and B, and done. Rather than 32, or what was it? 4 pages of SQL code. So it's optimized for that kind of scenario. So Neo4j in the real world then. What are you actually use it for? But before that, some background on Neo4j. It actually got started way back in 2001. Actually, we wrote the first prototype in 2000. So we've been at this for a while. We released the 1.0 version in 2010. So it took us 10 years to get to 1.0, which is because we're a database, so we obsess about robustness. That's the one thing that we obsess the most about. Anyways, we prototyped it way back in the days, in the early 2000s, when we worked at the media asset management company, which is like enterprise content management. It got released as an open source project in 2007. We got some seed funding for the company backing the open source project called Neo Technology in 2009. We were only an embedded Java library before, a jar file basically, a simple jar file, less than 500K, up until 2010. And that's when we released Neo4j Server, which is to old Neo4j sort of what Solar is to Lucene. So it puts it out on the wire. So that's sort of the quick background. And So Neo4j is a graph database, and I think that part is clear at this point, I hope, in the presentation. But what does it actually mean? So graph, the graph part of graph database means that it's a property graph, and we talked about this. It's awesome for complex, highly connected data, but it's also a database. And I would argue that there are some of my lovely friends, brothers and sisters in the NoSQL space, who I would challenge that they are a database. In my mind, if you store data in something and it can lose it after you've stored it, you can be many things, but you're not a database. And for Neo4j, we think that's absolutely, that must never happen. That's a showstopper. So we have actually ACID transactions, which, as some of you may know, is pretty controversial in NoSQL land, because in NoSQL land, you're supposed to be BASE, which is this other acronym, basically available, soft state, eventually consistent. It's a great acronym. And it basically means that you want to relax consistency in order to get to massive scalability, which I buy 100%. But my counter to that, though, is that you want to build an eventually consistent system on the foundation of a very consistent system. If you build a database, you want to build a highly transactional core that you then can choose to relax once you get into, hey, I don't have 3 machines anymore, I have 10 machines or 20 or 50 or 100 machines. Then it's always easier to relax consistency rather than start with relaxed consistency, and then after 4 years you realize that, hey, the mainstream use case actually doesn't require eventually consistent, and then you try to bolt on consistency, strong consistency. So that's why we've chosen to be completely ACID transaction. Have an ACID transactionality. I'm a Java 1, so I can speak my native Java language. We're a JTA compliant transaction manager, which means you can use @transaction in Spring, for example, and it's just going to work out of the box. We can participate in 2-phase transactions. We have really big customers using Oracle RAC on one side and Neo4j on another side. Put all the simple data over here, put all the highly complex data. Cisco has a massive master data management system up and running using this in production. And they use 2-phase commits between these two systems. We think that's great. We don't think that 2-phase commits is usable in every scenario, but that's always the case in engineering. So that's an important point. We scale up pretty well, 34 billion nodes and relationships and 64 billion properties. We scale out using a master-slave architecture, which means that we have replication. So all the data you write to one machine is going to get replicated out to all the other machines. We do not yet...
synchronization between remote locations.
The question is, do we support synchronization between remote locations? Well, if you put up a Neo4j instance here and one instance over here, and you ask them to join the same cluster, they're going to be synchronized. But if you mean it's like from my cell phone to the server, data centers, we do support that, but there's not, in this release, there's no data center awareness. What you ultimately want is saying that, hey, I run a cluster which is globally across multiple data centers. You want to say that these 3 instances that are local to you, replicate to them very frequently, and these 3 instances which are in another data center are not local to you, so replicate less frequently. And we don't support that yet. That is coming in an upcoming release, though.
But I mean, related to that, though, do you basically need less sharding if you support so many nodes, for instance?
So, yeah, good question. So the question is, do you need less sharding if you support so many nodes per instance? And sharding, as probably most of you know, is when you partition your data and put parts of your data on one machine and parts of it on another machine. I would say for size, it's very infrequent that you need to shard for size. This is more than a lot of people have. But the drawback of the master-slave replication architecture is that your write throughput of the entire cluster is limited by the write throughput of the master. Because every write needs to be propagated to everyone, and it needs to be, in particular, acknowledged by the master. And for that reason, you may want to shard. Good questions. Yeah, go ahead.
These statistics show that there's 34 billion nodes,
Yep.
34 billion relationships. This means that each node is connected only once.
Yeah.
So
Yeah.
this is a very shallow
Yes. If you would push it to its extremes, so let me put it this way. I've never seen a real-world example where people run into both the node limit and the relationship limit at the same time. Yeah, no, exactly. It's usually way less nodes because the nodes are typically connected to other nodes, and they scale like that. But that's an astute observation. Any other questions on this?
Is there any support for aggregating functions? Because now you're going more relationship-based, and two different nodes talking together, where you take data with them, where they're all in one place. When you want to calculate average data summary, it's all in one place, then you can deploy it.
Can you rephrase that question? I didn't fully understand it.
So things where you have group functions, things where you want to calculate sum across distributed. In a relational database, anything that is similar is all grouped up across in one single table, where it's easy to just integrate over that table and calculate those things. In a more relational graph database, you have distant points which are far away from each other. How do you group them and calculate them from group?
Yeah. So the question is, how do you, if you aggregate data and you group data, why won't you run into a situation where one node is here and another node is over there, particularly, and maybe even on a different machine? That's the question, right? Yeah. So currently, we don't support auto sharding. So all machines look the same. The graph on every machine is identical to the graph on every other machine. But then, however, on that instance, Neo4j is super smart about doing exactly what you said. So if data is very connected, very local, it's very likely to be both on disk and in memory be local. So that then those things will be really fast. All right. Yeah. So we've talked about this. It's now a server. Actually, our heritage is embeddable as a library on the JVM. So we have I'd say a very powerful and rich Java API. In the embedded version. And then we also have a server version, which uses a RESTful API, where you have client bindings in various other languages. And we've talked about high availability for read scaling as well. OK, so then what are graphs good for? So the answer is for any situation where you have highly connected data. And it turns out that there's an explosion of that today. The first one that got most people's attention was social. That's an obvious one. But recommendations is also a great example in retail. We have a lot of applications in finance. There's obvious applications in intelligence, in the intelligence community, in network management, in telecom, etc. We're going to talk about 3 real case studies. I actually noticed that there are older versions of the slides where we were not allowed to talk about the specific customer, but we are now. So I'm actually going to mention the actual customer names, and I'd be happy to put you in touch if you're close to the brink of putting Neo4j into production and want to speak with people who are doing that or have done that for some time. More than happy to put you in touch. We're going to talk about 3 case studies. The first one is the ACL from hell. So it's around access control lists. The second one is about recommendations, and the third one is global collaboration. So the first one is a big telco, top 10 telco in the world called Telenor, based in the Nordics, which is where we're from originally, even though now we're based here. And what they wanted to do is that they had a big system running on Sybase, where they stored all of the users, their entire subscriber database. They provided, their IT at Telenor, the telco, provided a utility for their high-end, their premium customers. Their premium customers are big brands like, let's assume IKEA, to use a Swedish example, right? Let's assume IKEA is using them. IKEA is they don't have 3 subscriptions with this telco. They have probably tens of thousands. So IKEA then needs a little web app to be able to manage all that and say that, hey, the guys in marketing are not allowed to make global phone calls, but the sales guys are allowed to do that. Click, click, things like that. And that ended up being a super big, complex hierarchy. You had subscription plans connected to devices, connected to people belonging to groups belonging to departments, etc. And they were stuck. They had minutes response times in their Sybase system due to joins because of connected data. And so they plugged in Neo4j and got millisecond response time. And they put that in production, I believe, a year and a half ago now. So that's one example. Another quick example is a big professional social network, the second biggest one after LinkedIn, called Viadeo, which is the French one. They have, again, this is old version. I think they have north of 50 million users today. So they're pretty huge. And they want to do basically the example that I talked about before, even though this was not the customer for the benchmarking scenario. But let's assume that I want to get in contact with someone. I want to figure out how can I get to that person. Should I go through my friend John or my friend whatever? And they want to show that visually on their page. It's a very similar operation to what we just talked about. And their initial solution was what everyone is doing, which is they put everything in their join table. Once the join started being too costly to do at runtime, they basically pulled together a small cron job, which once every hour did the joins, pre-computed them, and put them in a separate table. So I have one table called one friends, which are all of my direct friends, and another table called two friends, which are all of my friends of friends, and another table called three friends. And once every hour, that got regenerated. You know, not that bad. The problem, of course, was that that thing just took a minute initially, and then they grew, and then it took an hour, and then that grew, and then it took a day. And when we were there, it actually took, I'm not sure if I have that on here, 2 days. When we got in, it actually took 1 week to generate just those pre-computed tables, right? So they swapped in Neo4j and can do it in real time.
Yeah, but do they use it as a prime persistent storage for 30 million users?
I can't comment on.
Once a while.
No. So they're not generating it. They're doing it in real time. So if you and I connect as friends on Viadeo, then that millisecond, the moment that transaction commits and is in the relational database, it's also going to be in Neo4j. And if I immediately in another web browser, if I 1 millisecond after that query, I'm going to see the path through you. So it's completely real time. The third example is Adobe. One of Adobe's top level, if not most strategic initiative right now is the Adobe Creative Cloud, which is their cloud offering of all of Adobe's software. And part of it is a collaboration aspect where they say that, hey, we should allow our users to form ad hoc groups and collaborate on content. And this is going eventually to be a drop down in every Adobe product. You should be able to go in from, I actually don't know any Adobe product. What are their products? Adobe PDF readers. Photoshop, I guess, is a good product. Where you're working in Photoshop and you should be able to just upload it to the Creative Cloud and form an ad hoc group with someone. So you're going to have a lot of people, a lot of assets. You're going to form a group. You're going to disband that group. Very graph-oriented system. And it's all built on Neo4j across, they actually have 9 production instances right now. And they have 1 data center in Japan, 1 in Europe, 1 here in North America. So it's a completely worldwide deployment of this. Absolutely zero downtime. Absolutely zero downtime. Not a second of downtime per year is their requirements. Which has actually led us to the 1.8 release of Neo4j was released yesterday or the day before yesterday, and it includes rolling upgrades, which was particularly a welcome surprise for the Adobe team. And rolling upgrades is if you run a cluster on Neo4j 1.7, you can now bring in 1.8 on one slave and then on another slave and then on the master. You can roll your upgrades and never have any minute of downtime. Question?
Are you syncing all of those centers together, or customers just go to a certain center?
No, it's syncing all of them together.
Worldwide?
Worldwide.
So the syncing, is that asynchronous?
That is asynchronous. Between the master and the slaves, it's asynchronous. However, so our master-slave replication works very similar to MySQL's, which is that you write to one master, and then eventually it's going to propagate out to the slaves. However, a drawback in MySQL's, at least the preferred architecture for MySQL, is that you as a client will have to remember that this fellow over there, that guy is the master. Because if you write to one of the slaves, you're like, all hell breaks loose. When they start shipping transaction logs over, it's a really messy situation. In Neo4j, you can write to every one of the slaves. You can write to every slave or to the master. But what the slave will do, if you write to a slave, it's going to go over, find the master, grab a write lock, and do actually a synchronous write on the master, which is a strong consistency operation, like a small two-phase commit, although we don't use the XA protocol for that, obviously, because it's just between two Neo4j instances. And then once you've written the data to the slave and to the master, and the master says that it's okay, at that point, the transaction will return out and say, yeah, acknowledge this was actually written. Go ahead.
So you say asynchronous replication?
Asynchronous replication.
So it's not in the transaction. So if the master were to die, you would lose data.
If the master were to die, you would lose data, which is why we recommend people to write to the slave, because then it's also going to be at the slave. So then you have the equivalent of n equals 2 in Dynamo. So you have the data at least in two places. Okay, so that was my quick crash course. And the big question then that all of you are thinking is that, holy shit, how is this presentation so smooth and awesome? Now the only thing I want to do is screw this conference and just download Neo4j. Luckily enough, I have a slide on that. So what do you do if you want to get Neo4j? Well, you have two options. And in fact, I just realized that I removed probably the most prominent option, but we'll get to that. So the first option is go to neo4j.org and hit the big download button. You're going to get a zip file or a tarball, and you're up and running. The second option is you can try it out in the cloud. We are available on Heroku. It's super simple to get up and running. I actually did a presentation for a Ruby group just a couple of days ago. And my usual slides include a third option, which is Maven. But I didn't want to get into the whole, every Ruby programmer in the world is not super thrilled about Java. So I actually removed Maven because I didn't figure it was so pertinent to them. But that's the third option. And if you use Neo4j embedded, that's probably the preferred one. All this is obviously available on neo4j.org. I'm going to talk about that. Final thing that I want to mention is that if you think this sounds interesting, if you want to know more about graph databases, there's a conference coming up called Graph Connect, November 5 and 6, here in San Francisco. It's going to be an amazing conference. We have speakers from Twitter, from Square, from Adobe, from Cisco, etc., talking about how they handle, how they work with graphs, both tools as well as use cases and practices. There's managerial high-level tracks as well as really hands-on developer tracks. I think it's going to be an amazing conference. If you want to know more about it, please chat to me afterwards. And then finally, I want to wrap up with a quote from, it's a while ago now, but it's from one of the most, I think, clueful observers of the NoSQL space. Has done some of the best writing, I think, about scalable systems. And he says that, I'm going to play with Neo4j. It seems to me that even after arguments about ACID/scale/the CAP theorem, it's just more human and agile to be graph-based. And I really love that quote. So finally, I want to urge you all to go out and enjoy the last, I guess, afternoon of Java 1. But remember one thing, to be more human and be more agile and be more graph-based. Thanks, guys. I'm happy to take questions here or after the fact. Yeah, go.
So how many masters you have?
How many?
Master?
One master.
So it's single point failure.
The master is a single point of failure. If it does go down, it's a new master will be re-elected. And what we encourage people to do is to write to the slave so data is at least duplicated on 2 instances.
Do you have a plan to do like multiple masters?
Yes, we do. I can talk more to you about that later if you want to.
Like, what do you think?
Next year. Next year.
Okay.
Question in the back? You. Yeah. Are there the best practices around? About the replication delay? Yeah. Are there best practices? There's a bunch of people who have put it in production, and almost all of them use replication. So yeah, I'm not sure if we crystallized any best practices from that, though.
If I'm reading from one of the slaves, is there a way for me to find out whether or not an object or that database is behind other members of the cluster? Like in MySQL,
you can do that. We actually don't have that now, but it seems like a good thing that we should probably add. I'm going to take the final question, then I'll take questions individually. Yeah, go.
Is there a list somewhere of the graph theoretic algorithms that have been implemented on Neo4j?
We ship with some graph algorithms, but a really small, I mean, there's a gazillion of them, right? And those are listed in the documentation, docs.neo4j.org. Then obviously there's a bunch of them floating around, but there's no one master list for that, obviously. Thanks. All right, thanks everyone. Happy to take questions afterwards.